Okay, so here's a shear flow example that I put in the beam bending and beam shear review notes. So shear flow is a shear force per unit length, and we use this to design and space fasteners of composite members. And we have a couple equations. We have little q, which is shear flow. That's the shear force, times big Q, which is the first moment of the area, all over the moment of inertia. And then we have this equation where shear flow times the spacing has to be less than or equal to the number of fasteners in a certain area. So that would be, again, this kind of like tributary area here of S. So in this situation, our number of fasteners is going to be 2. And VF, which is the shear force of the bolt. And for this example, we're given that the shear force in the beam is 400 pounds, and the shear force that the bolt is able to withstand is 120 pounds, and we're supposed to find the max spacing. So the first thing we get to solve is what shear flow is. Little q. And q, so we're going to start here. So that means we know V, but we need to calculate Q and I. Okay, so to start with, the centroid of this is at, so if we have neutral axis, y equals 3 inches, and that's to top or bottom, symmetrical. Then it's easy to calculate the moment of inertia. I equals bh cubed over 12, and that equals, our base is 4, our height is 6, all over 12, and we get 72 inches to the 4th. Now, big Q. Remember, big Q is the first moment of area equals y bar. So that's from the centroid of the whole thing to the centroid of the area that we're concerned about. And for us, we're going to look at this top block. We could look at the bottom block. But ultimately, we're going to use this area here. This is our area. So our y bar is going to be the distance between our neutral axis of the whole thing at 3 and the neutral axis here of that top area. Okay, so y bar times the area. Okay, so we have y bar equals 3 minus 1. So the whole centroid is 3. The centroid to the middle of this area is 1. 3 minus 1. That's y bar. And then the area is this 2 inches here and that 4 inches there. So 2 inches, this is inches, times 4 inches. And we get Q equals 16 inches cubed. So now we can plug in everything for small q, shear flow. And we get Q equals 400 pounds times 16 inches cubed. That's big Q. So shear in the beam times first moment of area all over the moment of inertia, 72 inches to the fourth. That's that guy. And we get 88.89 pounds per inch. So then the maximum nail spacing is when we use this equation, because that's S. So we have shear flow times the spacing has to be less than or equal to the number of fasteners times the shear force of the bolt. We solve for S. It's less than or equal to the number of fasteners times the shear force of the bolt, or nail in this case, all over the shear flow. The number of fasteners here is just 2. We're looking at these 2 bolts. So remember how we're thinking about how many, this S, this is the area we're thinking about. So all we care about are two nails at a time. We don't take all of them, just 2 at a time in this case. So there's 2 bolts, or another way you can think about it is if you went back to how we calculated our area, focused here, we just had these 2 nails right there. So we have S, this is 2 nails times, they gave us shear force of a nail is 120 pounds. And that is all divided by the Q we calculated of 88.89 pounds per inch. And we get the spacing is less than or equal to 2.7 inches.